Hello everybody, this is the next video lecture. This is continuing from our last lecture when we were introducing hypothesis testing. We were going through the steps and sort of how to do it, but we didn't do a statistic yet. So in this second part, we actually are going to run a statistic for the first time. And what I'll say as we're starting this is something to keep in mind in general for this whole class, especially as we get to more advanced stuff in terms of inferential statistics, is to keep in mind that you might not get something right away. Don't get discouraged if you're not quite getting it the first time. Oftentimes we have to sort of present it, and then you do some examples, and you sort of get a little bit more. You do more examples, you understand it better. You do the homework, you understand it better. So don't expect that you would know 100% what's going on right away. Let yourself go through the process of going through some problems, practice problems in the lecture, and let yourself go through the process of the homework, and things should become clear through that process. And so in this lecture, we're actually going to do the first way to test the hypothesis. So we're not just going to talk about it, we're actually going to do our first inferential statistic. And what I'll say is this is actually more of a conceptual transition. So what we're doing today is not necessarily something that's used in real statistics in real life, but it's a transition from the z-scores that we just talked about, which are conceptual, to ways we actually do statistics. So this is kind of a baby step towards actual statistics that we'll use in real life. And we're actually going to branch out from the z-score, and we're going to call this a one-sample z-test. So your first inferential statistic is a one-sample z-test. And remember, this is a simple extension of the z-score that we just did. So remember, the z-score was this. I think I'm going to draw it. Just give me a second here. Oops. So this is a conceptual, so the concept, and this was the z-scores that we had done just now. Remember, the formula was the z equals the difference between a score and the mean of the distribution. But we don't, that doesn't matter. That difference doesn't make any sense unless we standardize it by dividing it by the standard deviation. So here we're going into a little bit more real situations, but I'm gonna erase this actually. We're just gonna do a one sample z. We're just gonna call it one sample z. And this is a little bit unusual because a one sample z is typically not the situation that we have in research. But again, this is also a sort of a conceptual baby step to real statistics. So this is a one sample z. We'll just say z again, but just know it's a one sample z. And so the difference is it's going to say that there's a mean minus the mean of the population. So a sample mean and the mean of a population. This might seem a little bit confusing, but basically what we're going to do is, and it's going to vary a little bit by our examples, but in essence what we're going to do is we're going to have the mean of a treatment group. So something happens that we think is going to change people's behavior. So remember from the previous lecture, treatment is the IV that you're manipulating, and treatment is the thing that you think is going to change people's behavior. And so if we think alcohol increases attraction, then that's our treatment. And I'm just realizing I don't know if I actually did the reveal from the last lecture. I don't think I did. So I'm going to do that right now. So why not? We don't have to do everything always in order. So the big reveal of the last lecture was that there is no such thing as beer goggles. So I don't know if I talked about this, but basically there's not beer goggles. They've done it experimentally, and also they did it in the real world and real world studies. So non-experimental studies, and they found no evidence essentially for alcohol increasing attraction to other people. So what's going on? Well, they couldn't really tell from the lab experiments because they're sort of artificial. And so from real world studies, so non-experimental studies, they found that it wasn't beer goggles, it was time goggles. So as the night got late, if you're in a bar, the bar is closing at a certain time. Or if you're at a party, the party is winding down, people are leaving, the party's going to end soon. People start feeling like, hey, if I want to meet somebody tonight, the options are reducing. And so they start reducing their standards a bit, and people start looking very good to them. And then the time pressure is what leads to increased attraction at the end of the night. It's not alcohol. So you can see that in the real world, those two things are confounding. So typically, the later it gets, the more alcohol people have consumed. So there might be an impression as the alcohol, but experimental studies and then real world studies, non-experimental studies, show that alcohol has no effect, and it's the time goggles. So this was brought up because we can think of this sample mean versus the population mean just simply as the mean for treatment. So if we have an experimental study where we're given alcohol, that's the treatment group, alcohol. So the mean attraction for the alcohol group. And then we have a placebo group. The placebo group doesn't get the treatment. Sorry about that. That's just a mean, that little X bar. The placebo group does not get the alcohol. So we kind of treat the placebo group, or sometimes it's a control group, but the placebo or the control group, we treat that as an estimation of the population value. Why? Because the population value is how people are naturally, in terms of how they're attracted to other people without the treatment you're talking about. In this case, the treatment is alcohol. So typically you see the formula, it says sample mean minus the population mean, but when we're actually collecting data, we oftentimes will say that the treatment group mean is the index of the sample mean here. And we're curious about whether that treatment group mean is different from the mean for the placebo group, which is an estimate of just how people are in general without the treatment, without alcohol. So we're curious if these two things differ. And the question essentially is, did the treatment change the behavior? So in the case of the beer goggles, did the alcohol increase attraction over no alcohol? And then the notation that we had at the bottom was the standard deviation over the square root of n. So remember that n is the sample size. I'll show you this. So square root of n. So it's the same as what we have here. The only difference is now we have a sample size. And this one, because we're actually dealing with real data, this is talking about population values, but this is real data on the bottom. So it's exactly the same as this. We're comparing two things on top, except the two things were here, individual score versus the sample mean. This is actually saying the sample mean compared to the population, which really is saying when we do research, is there a difference between our treatment group and our control or placebo group, which is estimating the population value of our dependent variable. So the top is the same. Just remember we're comparing two things. It's just that we're just taking it slightly different. And here we're actually taking a treatment group versus a placebo or a control group. And then the bottom is almost exactly the same, except here we're starting to talk a little bit about inferential statistics. So now we care about sample size. So now just instead of having standard deviation, we add that little divide the standard deviation by the square root of n. So why I'm going on about this is that they're basically the same formula. The only thing that we're doing now is we're adjusting for the sample size on the bottom by taking the standard deviation, dividing it by the square root of n. So the formula is pretty much exactly the same. It's just a little bit of tweaking. And since we're talking about inferential statistics, we don't care about a person, which is what the z-score was about. We care about our experiment, which is looking at the difference between, for example, a treatment group versus a placebo or a control group. I might keep that up just in case I want to use that. So let me go on to the next slide. And then the thing is, when we're talking about inferential statistics, remember we have that line. And so in the last lecture, I talked about that line. I talked about that 5% line, that the mean has to be so far for the treatment group, so far away from the control group or the placebo group to say that the treatment made a difference. And I drew that line that we had to cross to say there was some difference. That's actually the critical value. So let me draw that. Excuse me, I'm just plugging something in here. I'll have to get rid of this picture. So I'm just going to refresh what we talked about last time. So I'm going to draw this again as a normal curve. Because remember, those normal curves have all those percentages in it. So that's what we're really talking about in inferential statistics. So remember, we have a normal curve. Looks roughly like that. And remember, in the middle of the normal curve, we have the mean. And what I was telling you is that we take the placebo group or a control group as an estimation of that middle mean where people are without the treatment. So from our beer goggles example is that there's no alcohol. So what are people's attraction without alcohol? Well, that's right there in the middle. That's estimating the middle where most people's scores are without the treatment of alcohol. And then we talked where the treatment group had to be to say that there was a difference. So we kind of talked about, well, if it was here, if it was in this area or here or here, it's probably not far enough away from this mean. It's not very far away. There's a lot of scores still going on here. So there's still, it looks like a decent chance just by random luck that people would have scores like that anyway. So it doesn't really look like treatment. It just could be sampling error. And so for us to say that the alcohol had an effect, our mean for our treatment group, so this is the mean of the placebo group, should be way over here somewhere. It should be way over because we want it to be pretty far away to say there's a difference. So the mean of the treatment group, if there's evidence for alcohol influencing attraction, which it doesn't, I feel a little bit guilty talking about it because it doesn't, but this is our example. The mean should be over across this line. And we talked about, the normal curve, if we kind of look at the area here, this area that we were choosing actually is, there's only 5% of scores over here. So if you go to your Z table and look at your curve, there's only a few scores way off at the end, this high, that there's only a 5% of scores that occur there anyway. So if our treatment group crosses that line, it means there's less than a 5% chance it's just due to luck, which means there's a 95% chance it's due to the alcohol. So now we can start saying that we're 95% sure that if our mean for treatment group for the alcohol group crosses this line, it's that far away from the placebo, we're now 95% sure that that difference where it looks like the alcohol group has more attraction than the no alcohol group, we are 95% sure that that will apply to our population. So I'm going to go back to the thing here. So that's we call it a critical value. Critical value. You have to cross this line. If you cross this line, we'll say that the difference between the alcohol group and the placebo group's large enough to say something's going on in general. So we're going to treat that as a critical value. And we're doing one tail again, because one tail is we're saying that we're making a prediction that alcohol increases attraction. Two tail would just say, I don't know, alcohol could increase it or decrease it. I don't know. It's going either way. But we're making a one tail prediction here. And what's really nice is we can actually have a number here for our z-scores. So again, I'll sort of talk about this. So p is less than 0.05. What does that mean? Remember here? I said if we cross this line in the treatment group, the alcohol group's mean for attraction's way over here, that far from the placebo group, there's less than a 5% chance it would be so far above the placebo group that it would be due to chance. There's only a 5% chance, less than a 5% chance that it's due to sampling error, just random luck. So again, it means 95% sure alcohol had an effect. So that p is less than 0.05 means that there's just a 5% chance or less that you would have such a large score for alcohol compared to placebo that it would just be due to luck. So we know that there could be some sort of weird sampling error. We chose a weird sample, something weird happened in our experiment. We know that. But we can live with it if there's only a 5% chance or less of that difference being due to luck, because it means 95% chance is due to the IV. And then what's nice is we can actually get a number. So if we're talking about z-test, because now we're talking about that one sample z, so we can use the same table actually that we've been using, we can look this up. So actually I put a number here. I'm going to show you where I got that. And I'm going to expand this a bit, I think. And I can't expand it too much, but I can expand it a bit. And I don't know how to get rid of this add stuff. It looks like it's hard for me to see. So how did I get that? So remember that our p was less than 0.05. So remember, we're using a p of less than 0.05. Well, what did I do to find a critical value? Well, what I did is I went and I found, and this goes both ways. So if I'm using the positive z-score, I'm looking for this number. Why this number? Because 95% of the scores are below that number, 5% are above. So I'm looking for the z here, that 95% are below, 5% are above. So I'm looking for 0.9500. So 0.9500, I hope you can see this. You see where my cursor's right before the ads by Google thing? You see that there's a 0.94950 and there's a 0.9505. There's a 3 there, but usually they only give 4 decimal places. The z-score, where 95% of the scores are below and 5% are above for a positive z-score, is 1.6. You see it right here? 1.6. It's in the middle of these two, so 1.645. So the z here is 1.645. So the z-score here is 1.645. So if we do a one sample z-test on our alcohol group, our treatment group, versus our placebo group, no alcohol, on attraction, if we calculate that one sample z and it is 1.645 or above, we've crossed this line. So if you have a higher z-score, the higher z-scores are over here. So again, we'll do this. Again, you might not catch all of this right away, but we'll do many examples of this. So again, if our z-score, remember the z-scores go up as we go right. If we have a z-score higher than 1.645, then it means we have less than a 5% chance of saying that the alcohol group is greater than the placebo group, and that's just due to dumb luck. It's unlikely to have a score this high, less than 5% chance. So that's where our critical value comes from. You can see it directly from the table. What's nice about these one sample z's is that critical value does not change. So we don't have to go to the tables all the time now. That 1.645 is always the same. The only little tweak that we have is whether it's a positive z-score we're looking for or a negative. Positive z-score means that our treatment group we think will be higher than our placebo or control group. So in this case, we think that the alcohol group, the treatment group, is higher than the placebo group on attraction. Therefore, it's going to be a positive z-score. Let's just say that we do another study. I'm going to sort of put it off over here, this little box. We're going to do another study. And I'm thinking, I don't think I'm going to just draw it. So just saying, let's pretend. So that's when we're predicting that the treatment group is higher than the placebo group. Alcohol increases attraction over no alcohol. But let's say that we have another study where we think the treatment group is going to be lower. So we have our normal curve. We have a mean here. And this mean for our population, maybe I should put this mu. In some ways, it's like a population mean. The mean that we're estimating for the population, where most people are going to have their scores around here, is from a control group or a placebo group. So we always kind of start there. So in the other study, we said the mean of the treatment should be above. Let's do one that the treatment should be below. So let's look at depression. So let's say that we have a new medication that treats depression. And so when we do our study, we will hope that our treatment group, our medication group, will have lower depression scores over here on the left than the placebo group that didn't get the medicine. So in this case, we're expecting our mean for the treatment, so our medication group, will be less than the mean for the placebo. That would mean that our medication decreased depression, had lower scores on depression. And the logic is the same. So, if we had a mean for our medication group here, or here, or here, or here, we would say it's probably not that much different. It's pretty close to the mean for the placebo group. It looks like the medication didn't have a large effect. Maybe it is less depression, but it's probably not big enough to say that there's really an effect there. So we would really want, again, that same kind of line. We want a line right here. So if we drew the little area here, there's only a 5% chance that depression for our, and this is the treatment group, so our medication group, there's only a 5% chance that that group would be so much lower on depression than the placebo group just due to chance. So that means that we're 95% sure that that depression was decreased because of our medication, and therefore we're 95% sure that this finding that our medicine decreases depression in people, that this sample's data applies to the population. We're 95% sure that we can make conclusions about how people would react in general to our medication based on our sample's data. And this is the same thing that we have. So we have a p is less than, we'll say again, remember that p is always going to be less than 0.05. That's going to be a standard that we're always going to use. It's just saying that we are okay to live with a 5% or less chance of making a type 1 error, of saying that, yes, our medication made a difference, but it was just due to chance. We know there's a 5% chance for that. That's okay. We set that in psychology all the time. We can actually look up the z-score here. So remember, the z-score for the positive was 1.645. Well, if you remember, one of the big qualities of a normal curve is that they are symmetrical. So that p is less than 0.05, it doesn't matter whether it's a positive z-score or a negative z-score, it's going to be still 1.645. It's just negative in this case because we think that our treatment decreased depression compared to the placebo group. And I'm going to go to the table. I'm going to show you that that same number comes up. So here's our table, and we're going to go to the negative z-score, and I think I'm a little bit off here. There we go. So we're going to go to the negative z-score. And in this case, we're just looking for this number. We're going to be looking for this number. Why this number? Because we're looking for the number for a negative z-score where there's just 5% of the people here. So we're looking for 0.0500. That is the proportion for 5% of the people right here, the thing I'm shading. And that's, that's what the table is giving us, right? So our table is giving us this, that little shading area, and we want that shading area to have 0.0500. So let me go ahead and look for this. I think the ads got bigger. These are kind of annoying. I know that's going to maybe mess things up. Dummies. Okay, hopefully you can see that. I still like this table. It's just annoying dealing with those ads. Maybe I can do it now. There we go. I might even get bigger. I might be getting greedy. I got greedy. Okay, there we go. So we're looking again for 0.0500. So we're looking. Oh, look at here. So we have 0.0505, and we have 0.054947. We can round it up to 495. So the 0.0500 is between these two numbers. Well, what are those two numbers? It's negative 1.64 and negative 1.65, and so in between it is negative 1.645. It's the same number. It's just it's negative. So 1.645 is the magic number, the critical value for one sample Z. And I'll get rid of these. And the only difference is it's positive if you think that the treatment group should be higher on a dependent variable than the placebo group. So if you think alcohol increases attraction over the placebo group, it's a positive z-score. It's a negative z-score for your critical value if you think that your treatment group is going to be lower than your placebo group on the DV. So in this case, we hope that our treatment group has a mean level of depression that's way low. It's in this area compared to the placebo group. So it's a negative 1.645. So if our treatment group crosses this line and therefore is that much more or less on depression compared to our placebo group, then we can say that we're 95% sure that these findings that our drug works in decreasing depression applies to the population. And we only have a 5% or less chance of making a type 1 error where we're saying that something happened and it didn't. So hopefully that's understandable about what a critical value is. And again, we're going to be doing this quite a bit. So if you're not quite catching it now, you'll catch it as we go on. And so I'm going to continue, kind of mindful about the time a little bit. So, okay, so this also goes into the category of, we're going to talk a lot about this throughout the rest of the course. So if you don't fully get 100% now, it's okay. So when we're doing our inferential test, there's something called assumptions. Assumptions basically mean that the test works well under certain conditions. If you violate those conditions, the numbers may be off and you might make a wrong decision because you've done something that doesn't fit the mathematical model that we're using to make those predictions of p is less than 0.05. So there could be something about your distribution, about other things that could throw off, again, your ability to make those very confident percent probability statements of we're 95% sure that the sample's data applies to the population. So the first assumption that's true for most of the tests we're going to talk about is random sampling. Why is that? Is because you want to make sure that your sample is representative of the population and it's not some sort of weird subgroup of the population. But I'm going to sort of tell you about the reality of research, especially in social sciences. We violate this all the time. So if we want to talk about people, which we often do, we never come even close to having a random sample of everybody in the world. That's impossible. So the random sampling, we usually violate, but it's not that big of a deal. Why is it not that big of a deal? Remember the central limit theorem from our first lecture of this unit? That central limit theorem kind of basically says that, well, if it's not really a random sample, it probably doesn't even matter because central limit theorem will always drive us towards the normal distributions. And so, sorry about this, I keep on checking the time. Independent observations. What does that mean? Well, statistically, we say that error should not be related. So what does this mean? It's a little bit confusing, and I would bet you many people don't really understand this who are actually teaching statistics. But really, you have to think about methodology. So remember that in our methodology, if we're doing an experiment, a lot of this sort of assumes experimental designs. The only thing that is varying is our independent variable. We don't want anything else, an extraneous variable, changing while we're doing our study, because that extraneous variable could change people's behavior. And what's worse is if we have a confound where something is changed exactly with our IV, such as the expectancy effect. So in our beer goggle study, if our experimenter knows these people are drinking alcohol, these people are not, they might act differently towards them, unconsciously even. They might not be aware of it in a way that might change their attraction ratings. This is basically what this means. Independent observations. There's nothing else kind of throwing off your data. The only thing that's going on is the effect that you're looking for. Whether you find it or not, that's up to your data, but nothing else should be affecting your dependent variable measures except for your PV or IV. So that's why it says it looks random. Random means that there's nothing else. There's no third variable messing up the relationship between alcohol and attraction. That's really what that means. I'm going to take a small break and I will be back, but you will not notice it. And so let me sort of wrap up that last point by talking about it statistically. So I just talked about the method part, which is really the core of the whole idea. But why is that important statistically? So remember, statistically, if our statistics right and we make the right decision, the only thing that's pulling higher or lower our attraction scores is whether somebody has alcohol or not. But let's just say that there's that confound where our experimenters are acting in a weird way if they think somebody has alcohol versus the placebo group. And so if that's happening, then something else is pulling the data, pulling the attractions in different ways. So that's a problem with our statistics, because our statistics, our hypothesis is testing, is the alcohol making the changes? But then this third thing comes in, and that thing is actually pulling the data up and down because the experimenter is acting differently towards the people. So what we're saying with that is that that's happening. If there's errors that aren't random, errors are changes in the dependent variable, attraction goes up or it goes down. If it's going up or down because of something else, not the alcohol, it's the experimenter acting different. If that's happening, then we're going to make a wrong decision in our statistics. So we might say there was an effect, but really it wasn't an effect of alcohol, it was the effect of the experimenter acting weird. So that, in that case, we would make a wrong decision in our hypothesis test. And so the next assumption, it's an interesting one, and it's complex, so if you don't get it right away, we're going to talk about this a lot. I should say a lot, but for every statistic almost we have the same assumption. It's called homogeneity of variance. What does that mean? So remember, variance is how much people differ. So let's just take our study. So people differ on attraction, right? So people differ on attraction in everyday life. Some people are picky, some are not picky. And so what homogeneity of variance says is that the standard deviation, essentially, that's a measure of variance. Standard deviation for our placebo group without the alcohol better be similar to the standard deviation of our alcohol group. So that's the first point there. The how much people vary in their attraction shouldn't be affected by the alcohol. So if alcohol makes people shrink in terms of how much they vary from each other, and then everybody just is in love with everybody and they don't vary much, everybody is a 9 or 10 to the drunk people, that would be a problem. So that's homogeneity of variance, that our treatment group and our placebo or control group has roughly a similar standard deviation as a measure of variability. The good news about this, and we'll talk about this probably later too, is that our statistics are pretty robust against this. Robust means that this thing has to be really violated. So typically the standard deviation between the two groups, it has to differ by more than 4 times. So let's say that the treatment, or I'm sorry, the placebo group, people just differ by 1, let's say. So, just an average difference between people is at 1. So, most of us are in the middle, and most of us see people as a 6 or a 7. There's a 1 difference. If our treatment group, our alcohol group, had a difference of 4 points, that would be a big problem. So if they had a standard deviation of 4, that would be a big problem. Or if their standard deviation was a quarter of a point only, it was so much smaller than the placebo group, that would be a problem. In reality, that rarely happens, and so this homogeneity of variance, you need to check it, but we aren't going to check this, but if you're doing actual research, you're supposed to check this. But the reality is that it takes a lot of difference between your two groups in terms of standard deviation for this to throw off your stats. So typically, the statistics are robust. You can still do them with small violations of this. And then the final assumption that most of our tests have, that we're going to talk about in the class, is there's a normal distribution. So we're going to talk more about this as we go through the different tests, but we've already talked about how important the normal curve is in terms of making those probability statements in our inferential statistics, the probability that our samples data applies to the population. So that all relies on a normal curve. But the normality stuff, it varies by the statistic. There's different ways to measure this. So these things are things we're going to talk about throughout the course. So this is just your first taste of it. So if you're not quite understanding it, don't worry about it. It will hit you in the gut. I know that's a weird metaphor, right? I guess, yeah, that's probably the right way. It's either hits you in the gut or it hits you in the head. So you choose where you want to be punched by the statistics, whether it's in your gut or in your head, but no low blows. So hypothesis tests. So we're going to talk a little bit about what things affect whether our test comes out to be significant. Significant means that there's a difference, for example, between our treatment group and our placebo group. So the first point there is pretty easy. It just says that we have a larger difference between the treatment and the placebo group. I already erased it. So remember I'm just going to put this up here. Remember our formula. I'm going to bring the formula here so we just have it handy. So remember our one sample Z is simply, I'm going to put both formulas down here. Sample mean, population standard deviation divided by the sample size. But in reality, in how we actually do research, we might have the treatment group mean minus the placebo mean, the placebo or the control group mean. So our placebo group, so We're just asking, does the treatment change people's behavior versus not having the treatment? Does alcohol increase attraction versus not alcohol? And we can only judge that difference if it is a big enough difference by standardizing it with the standard deviation. But now we're starting to talk about real research with inferential statistics. Now we care about sample size. Because remember that the more pieces of information you have, the better your predictions are going to be. So if you go out on 20 dates with somebody, you're going to make a better prediction about them, whether they're going to be a good boyfriend or girlfriend, versus going out on one date with them. More pieces of information, the better your prediction. So that's why we start accounting for the sample size. Sample size is the number of pieces of information we're making our estimates on from our sample. And so this first point is just the size of the difference on top, this thing. So the first point is just talking about this. I'm reluctant to make a big mark. I don't want to mark up the whole formula, but this difference. So in essence, this difference between our treatment group and our placebo group, the bigger that difference is, the larger our z is, correct? So the bigger the top, the bigger the numerator is, the bigger the z is. So the bigger that difference is, it's going to increase our z. Our z is going to go up. If our z is going to go up, it's more likely to cross that line of the 1.645. So we need a z that's greater than a 1.645, absolute value of that. So the more our z goes up, the more likely we're going to cross that line. So that should be pretty straightforward. I know the statistics makes it seem more complicated, but duh, if you have a bigger difference between the treatment and the placebo, then more likely that means that something's going on in your treatment. The alcohol increased attraction, or the drug decreased depression if you have a bigger difference between those two groups. That's what that first point is saying. And then the second point is saying that the more variability, your z-score goes down. So I'm actually going to erase this because we're going to go down in our z-score. So the larger the variability is right here. And I'm tempted to erase this and this. So now we're just looking at variability. Variability is our standard deviation. It's on the bottom, it's on the denominator. The larger our denominator is, the lower our z-score is. So if you just want to think mathematically, the larger this is, so the larger our denominator, our variability, our standard deviation is, the larger our denominator is, the lower our z-score is going to be mathematically. But let's think about this conceptually. So the more variability there is, the harder it's going to be for us to make a confident statement about what's going on, because people are just varying in general. So let's just say that people are varying a lot in their attraction. We do our study and we just look at people in general and they're varying a lot. But what's wrong with that? Well, what's wrong with that is that even if we get a big difference between our treatment group, our alcohol group, and our no alcohol group, the placebo, even if there's a relatively big difference there, it might not be any bigger than this big standard deviation because people are varying a lot. So remember, it's the ratio. It's not necessarily just this. It's just how big is this compared to the standard deviation. So if the standard deviation is big, conceptually, even with a big difference between our groups, that could just be because of random chance, because people just are different so much on attraction, regardless of the alcohol or not. So bigger standard deviation, more variability. It's going to be harder to find an effect for your IV. Why? Because your z-score goes down. Oops, I'm going to erase this. There's one other factor, and I find it might be nice just to kind of clean up these things. So what's the third factor? So it says the number of scores. So remember, what are the number of scores? What does that really mean? It means the pieces of information that we're making our guesses about the population on. So just like dating, so if we go out on one date, our predictions are not going to be that good about the person. We go out on 20 dates, our prediction is going to be a lot better. More pieces of information, the better our predictions, conceptually, mathematically. The larger our sample size, more pieces of information, the lower our standard error. So remember in the central limit theorem lecture, the more samples, more pieces of information we had, our standard error went down. So we made less errors, we made better predictions mathematically. So here's our sample size right here. Whoops, I got to turn this back on. So our sample size is here, right here. What happens if our sample size gets larger? This bottom number gets smaller. So n goes up, this denominator goes down. If the denominator goes down, guess what? The z-score goes up. So this is bigger, this is smaller. I shouldn't say this is bigger, this stays the same, but the bottom gets smaller. That bottom gets smaller, the denominator gets smaller, what does it lead to? It leads to a bigger z. So again, we want a z-score that's greater than 1.645 to say something's going on. So the larger our z, the more likely we're going to say that there is something going on with our IV. Alcohol is making a change in attraction, or depression is changed by our medication. So those are the three factors. So how big is this difference on top? The bigger it is, the higher the z. The bigger the standard deviation is, more variability, the lower our z is. And the more pieces of information, the larger our sample size is, that will decrease the bottom, that will increase the z-score. So this is what this is talking about. And this thing that we're talking about actually applies to all of our inferential statistics that we are going to look at in this class. So these three factors influence our statistics sort of equally for the rest of the semester. So again, we will cover this more later. So if this is, I hope that you're getting a little bit of this, but if you're not getting everything, that's fine. It will click as we do more of our stats. We're just starting inferential statistics just now. So here's a question. So we're testing a hypothesis. And don't worry about the hypothesis. It's a little bit weird the way that they write it there. So what's likely for us to reject the null hypothesis? Rejecting a null means we reject that there's no difference. Remember, the null hypothesis says there's no effect of our IV. So by rejecting the null hypothesis, it means that we find an effect. So our IV is having an effect. Our medication decreased depression, alcohol increased attraction. So what combination leads to the best chances of us rejecting a null hypothesis and finding an effect of our IV? Okay, I hope you made your choice, A, B, C, or D. So here, check your answer. So remember, the larger our standard deviation, the more variability, the bigger the denominator, the bottom part of the z formula is, the bigger the bottom is, the lower our z is going to be. So we want a smaller variability, a smaller standard deviation. So for that first part, we want to say 5 for the standard deviation, not 10. Smaller standard deviation is going to help us find an effect. And then remember, sample size, n. So the more pieces of information we have to make our predictions, the more confidence we have in making our conclusions. So we're more likely to be more confident in saying there's effect if we have more pieces of information to base our guesses on, our probability statements on. And remember mathematically that as n increases, it decreases the denominator, the bottom part of the formula. So the bottom part of the formula is the standard deviation divided by the square root of n. So the larger n gets, the more people we have in our sample, it reduces the denominator, and then that increases our z-score. So larger z-score is more likely to reject the null hypothesis. We're more likely to get a z above 1.645. That means there is an effect for the IV. So smaller standard deviation, higher sample size. So we already talked about this. I'm not going to talk more about this. We are going to do a one-tail test. It's going to be greater than or less than. So greater than, alcohol increases attraction over no alcohol, or less than, our drug decreases depression over no drug. So you don't actually have to read this stuff. So let's just skip this. We already know it. We're well ahead of this. All I'll say about this final slide here is that the standard statistics book, and even, I hate to say, the standard method book in psychology, talk a lot about two-tailed tests being the best. So the only thing I'll say about this in favor of a two-tailed test is that it's harder to find a difference. That's probably the only argument you would have to do a two-tailed test, and I'll show you why. So here's a two-tailed test. So remember that we're always going to find 5%. So in a two-tailed test, you're going to have 0.025 here and 0.025 here, because it's two-tail. Your two tails have to add up to 5. Remember, our alpha is p is less than 0.05. There's less than a 5% chance that you'd be so far away from the middle, from the mean in the middle, that it'd be only less than a 5% chance due to luck. We could find that in our z-scores. The two-tailed test, you have to divide that into two parts. And so what that means is this line is further away than a one-tail. Because you've had to split it into two. Because if you're at 0.05, it'd be a little bit over this direction. Not severely, but it'd be a little bit over here. And this is probably very severe. This is not accurate. I just have to draw it this way. So the line to cross is farther away. So just think about that. The line that you have to cross, that you're far away from the mean in the middle, is farther away for a two-tailed test, because you've split them into two parts. For a one-tailed test, remember we have a 0.05 right here. So it's all in one tail. So all of this that's here and all of this is here is just added together. So this tends to push out the line a little bit more. So it's a little bit closer. So you don't need as big of a difference from the placebo mean in the middle to the treatment mean, because all the 5% is all in one tail. And so that means that the line's pushed out a little bit here. So the two-tail people, two-tail, one-tail, I think can only sort of say this because it could sort of push out more, and they can say it's more conservative if it's harder to find an effect. Therefore, you have more confidence in it. I think that's probably the only argument in social sciences. Other disciplines, so science disciplines, use two-tailed test. And sometimes that's fine, because maybe in some science disciplines, they're just trying to find something that's going on. They might not have a prediction of where it's going. They're just looking for some signal something's happening. So there's some signal here, and it doesn't matter if it's lower or higher. There's just something that says something's going on, and maybe that's what's important for some disciplines. In psychology, for example, that's not really great, though, because we want to make a prediction. We want to say, listen, our theory says it's going to be more. And if our theory is wrong and it's actually less, even if it's way over here, we say we're wrong. Our theory is wrong. And we have to have a new theory that explains what's going on. And so, in my opinion, it's a much fairer test, because you're placing your bets on one side or the other. And if you're wrong in the other direction, you are wrong. And what's really kind of a bad thing in psychology, if you do a two-tailed test, I believe, and you don't have a directional prediction, is you make up stories. You thought it was going to be this way. You thought it was going to be larger, but in reality, it went this way. And so you make up a story. Well, it happened this way because of this. That's not really good in psychology. In psychology, we have a lot of problems if you start making up stories after the fact. It's what we call theory fitting. You look at your data and then you change your theory to try to fit your data and say, yeah, I kind of knew that was going on anyway. So in my book, at least, one-tailed tests are better because you have to say what's going on. You have to have a strong theory, a strong prediction of direction. And if you're wrong, you'll live with it. You're not allowed to make up some story afterwards if it goes the other direction. So this is why I push for a one-tailed test. Also, the one-tailed test has more power. We call it power. What does power mean? Power means that we're able to find an effect that's there. Two-tailed test, you might miss something. It actually might be going on, but you miss it. So you do a type 2 error. You have a false negative. You say nothing's going on, but there really is something going on. So there's something to be said to have a little bit of push this direction legitimately. It's a legitimate push because you still have a 5% chance of losing or I shouldn't say losing, you have a 95% chance of losing. So if you end up, anywhere in this end, you are wrong. So it's still a fair game. There still is that 5% versus 95% chance. And there's only a 5% chance that you would be right by luck. So you're not doing anything. You're not changing the percentages of being able to find something. You're not tricking the game. It's just that you have more power. So if something's going on, you have a better detection of it because the critical value is going to be a little bit lower here. So I think that's it for that topic. These are pretty deep topics, actually, to start with our hypothesis testing, but your book goes over this, and this is the core of what we're doing. So in our class, we are going to do a one-tailed test. Never mind, but you already know this. You don't need to take that little test. So let's actually do a one-sample z-test. Let's actually have some data. So remember, here's our formula. So let's do an example together. This one's a little bit easier because we actually are going to just sort of state what the population mean is, and we'll say what a sample mean is. So we actually just take one sample. So the idea is that somebody says that, or let's say there's a report published somewhere that the average salary of a high school graduate is $39,000. So that is a statement of the population value. The population mean is $39,000. Let's say that somebody claims that that's not true. The salary is actually less than that, and they collect data to test that claim. So step one, remember step one was stating our HO and HA. In this case, the HO is the population mean is 39,000. So the population mean is 39,000. That's the HO in this case. The HA is that it's less than 39,000. So less than 39,000. That's the HA. We're going to use more of a sort of a research example in the next example. Let's just take this one first, though. So what that's saying, and I'm going to draw this so people are following this. And in essence, what we're saying is that we're saying that the population value is 39,000. So that's stated in the HO. The HA is that it's going to be less, and the less is going to be way over here. So we're going to say that it's going to be less than 39,000. And we know that we have to be way over here to say that it's actually less than 39,000. It has to be a lot less than 39,000 to say that there actually is a difference. It's just not some sort of random chance. And then our second part here, so that's our HA. Our HA is it's less. That's represented by that little shading on the left that we just did. So remember, step two is we set our criteria. Remember that our alpha is always 0.05. What's 0.05? What does that mean again? Well, our alpha is that the probability of us just by chance finding an average salary for our sample so much less than 39,000, there's only a 5% chance that it's due to luck. So there's a very small chance that it would be due to luck if we cross this line. So there's only 5%. There's only 5% of scores over here in this area, as we saw from the z-table. And remember that this line, this critical value, we're going to call it critical value. The z is, and it's negative. Why is it negative? Because we think our sample mean is going to be lower than our population mean, so it's negative z. Remember, our z is always 1.645. Why? That 1.645 is that line where there's just 5%. 5% here or 5% here if we're doing the other direction. But we aren't doing it, so I'm going to erase that. It's not a two-tail, but that's where the 1.645 comes. So the z right here, this line, still erasing, this line is the z where it's 1.645. So we want a negative 1.645. So when we calculate our z-score, we want it to be in this direction. We want it to be less than 1.645, which means that it's going to have a number that's, let's say, 1.7. So negative 1.7 is greater because we get bigger negative numbers. So there's more negative numbers this direction. So that's what we want. You can think about it as absolute values. As the z-score gets higher, the further we are away from the mean. Remember, in the middle, the mean is 0. Then we have 1, we have negative 1, we have 2, we have negative 2. So it's really the absolute value of the number that's the most important. So the bigger our absolute value of the z-score, the further away we are from the mean. The further we are away from the mean, the more evidence we have that there is a difference between our sample and the population in this case. So let's go ahead and let's calculate this. So we're given everything. So we're given the population mean. We have a sample here, so we took a sample. Our sample had a sample size of 100, so we need n for our formula, so we have that. N is 100. We have a mean, so this is a sample mean. Our sample mean is $37,000. And then the last thing we need for our calculation is a standard deviation. So the standard deviation of our sample is 6,150. So now we have everything for our formula. Remember, our formula is sample mean minus the population mean divided by standard deviation divided by the square root of n. Here's our sample mean, 37,000. Here's our population mean, 39,000. Here's our standard deviation, 6,150. Here's our n, 100. So we just plug that there. 37,000, 39,000, 6,150, 100. We plug it in. So step number 3 in hypothesis testing was we calculate our statistic. So the top part of the one sample z is the sample mean minus the population mean. So on top, the numerator is negative 2,000. So we're in the right direction. Remember, we made a one-tailed prediction that it's going to be less than 39,000. So we are in the right direction. And then the denominator, the bottom, is the standard deviation, which was 6,150 divided by the square root of n. So 6,150 divided by the square root of 100, which is 10. So our denominator is 615. So we take our numerator, negative 2,000, divided by our denominator, 615. Our z-score is negative 325. Looks like good news. I'll show you why. Where is negative 325? It's way over here somewhere. It's way over here somewhere. So this z of negative, I want to double check it, 325. Yep. 325 is way over here. We crossed the line. We crossed the line. We're further away than we need to be. We're further away than this 1.645. So we have a bigger difference than we need to say there is something going on. That's a good deal. And so we actually are going to reject our HO. And we can think about it this way. So remember, rejecting HO says there's something going on. HO says nothing's going on. If we reject that idea, something's going on. So step number 4 is what we just talked about. We actually make a decision about our HO. So remember that our criteria was negative 1.645. That was our critical value. That's the critical value that we set up beforehand, before we got our data. Our z-score actually crossed it. It's way over here. So we had a bigger difference than we need. So we actually have a nice decision here. So what we do is we take the number we calculated. Remember, we got this. Negative 325 is what we calculated. That number is greater than our criteria that we set, the 1.645 that we always have. If this number is greater than the number that we set, the number that we calculated is greater than the number that we set beforehand from the table, we reject the HO. There's evidence of an effect. Again, our z-score is way over here. We crossed a line. It's even further than we need to be from the mean in the middle to say there's a difference. We've crossed that line. We're pretty far from the mean in the middle. Something's going on. There is a difference. Then we write it up. Step number 5 is writing it up. So we just write it in words. And we're going to do it slightly different from the next one. We actually have some study. We actually have a study in the next one. But here we could say that the average salary of a high school graduate is less than $39,000. We want to get the mean of our sample. So the mean of our sample was 37,000, remember? We want to get the standard deviation of our sample. That's 6,150. So we just say in words what we found. The average salary of a high school graduate was less than 39,000. Well, for our sample, what was the mean? What was the standard deviation? Then we put a comma, and then we say our statistical stuff. So our one sample z equaled negative 325. That's what we calculated. Remember? Our z that we calculated was negative 325, so we say that. One sample z equals negative 325. This last little part here, this p is less than 0.05, it just means that that's a significant difference. There's less than a 5% chance. There's less than a 5% chance that we would have a salary so much lower than 39,000 that it would just be due to chance. There's less than a 5% chance you would have such a low salary, less than 39,000, just due to chance. So there's probably something else going on. There's an effect going on. So I know that's your first example, but hopefully that's relatively clear. But, don't worry about the write-ups and things like that. All this stuff we're going to be doing a lot, and it's just going to take some practice. So just remember the steps. I'm going to go over this again. Steps was to state your HO and HA. Step 1. Step 2 is state your alpha, and I'll just give you a little hint here. For all of our one-tail z, it's going to be the same. It's going to be a 5% chance that we're going to find something due to luck. That's our alpha. That's the small area on the extreme of the normal curve that we shade and say there's only 5% of the scores there. And the line of the z-score that crosses that is 1.645. It's negative 1.645 if we say that something's less than. So this one, HA, was less than. Or if we say it's more than, it's going to be a positive 1.645. But it's always going to be 1.645. Step 3 is we take our data, we plug it in. We calculate our z-score. Once we calculate our z-score, we take that z-score we calculated, we compare it to 1.645. If it's greater than that, we reject the HO and say something's going on. If our calculated z-score is less than 1.645, we say fail to reject the HO, and there is no difference between the population mean and the sample mean. And then we write it up. We start off by trying to say it in human words, And we give things like mean and standard deviations for groups or samples. We say what our statistic was, one sample Z. We say what we calculated. And then if we reject the HO, we say P is less than 0.05. P is less than 0.05. It just says that there's less than a 5% chance that we would find an effect. So really, there is an effect going on. Something's going on. So again, this is our first inferential statistic. If you're not quite getting it, don't worry. We will have more examples. So let's do one. And I'm going to have you do this on your own. So I've actually helped you out. I actually have a little bit of HAs here. But I'm gonna talk about it a little bit. And actually, I gotta edit this. Sorry about that. So I'm gonna help you out a little bit because research depends on having an HO and HA. So why not give it right away? So let's say that we have a study, and someone believes that narcissists are more aggressive when their ego is threatened. And sorry about this. Versus when not threatened. So you know what ego threat means? It just means that that somebody says something and you take it personally. So you take it as a personal slight to yourself. And so narcissists are what we call brittle. So if you say something that's different from what they believe, they get very defensive and start calling you names and get very aggressive. So again, the idea is that narcissists are more aggressive when their ego is threatened versus when it's not. So if you tap away at their sense of being better than other people, so narcissists think they're better than other people. They think that they're smarter than other people, that they're geniuses, and other people are stupid and not worthy of them, and they're the smartest person ever in the world and greatest person ever in the world. That's a narcissist. So there's a lot of research and theory actually that suggests that narcissists are very aggressive when you chip away at that idea that they're the best person in the world or the smartest person in the world. They're very sensitive. And then they're less aggressive when they're not threatened in terms of their ego. So I already did step one for you. So step one is the HO is that for narcissists, ego threat versus not ego threat, it's equal on aggression. So aggression is equal for narcissists under ego threat versus not ego threat. There's no difference. They're equal. So there's no difference. So remember, the HO says there's no effect. There's no difference. HA says that what we have up here, this is what we believe based on theory, etc., that narcissists are more aggressive when they're in conditions of ego threat versus not. So in terms of aggression, ego threat's going to be greater than not ego threat for narcissists. And so let's say that we don't know what the population value is. So we're actually going to run a group that's a placebo group to estimate aggression for narcissists just in general without ego threat, without the treatment. And let's say that we have that placebo group, we have a mean of 60, standard deviation of 10. And then we have narcissists under ego threat. And so we run them and we have, whoops, don't know why it does that. So we did, let's say, a sample of 50 narcissists. And don't worry about, oh, so we have 50 here. So we have 50 narcissists here. And we have a mean of 77. The mean is for aggression. The mean aggression with ego threat for narcissists is 77, standard deviation of 10. What I'll say is when you compute this, use this as the n and use this as a standard deviation. So standard deviation I set to be the same, so it's not confusing. But use 50 for the n. Don't use 100. Use 50. It's about one sample. This is our one sample. These 50 people were just meant to estimate the population value of our mean and our standard deviation. So use the n here and the standard deviation here, but that's the same 10. And I'm going to set this up in terms of what it looks like. So it looks like this. So remember, this is our population value, but we're estimating that with a mean of a placebo group. The placebo group here is there's no ego threat. So this number was, I'm going to look at this again so I get it right, is 60. So the mean level of aggression was 60. So no ego threat, the level of aggression of narcissists with no ego threat was 60. Again, we're estimating the population mean from that. And then what we're going to do is we're going to ask whether this mean value, so remember under ego threat is 77. So we're going to ask where 77 is. The mean of 77, does it cross this line? Does this cross this line? Again, remember our criterion, step 2 I did for you. Remember, step 2 is always going to be the same. It's always going to be the same for all of our 1 sample Z. There's our alpha is going to be 0.05. Our critical value is 1.645. What does that mean? So there's only a 5% chance that if you cross this line, there's only a 5% chance that you would be so far, so above the aggression level of the placebo group that it would be due to luck. So we're 95% sure it would be due to the ego threat condition. And remember that our critical value, this line we have to cross, is the Z has to be greater than 1.645. 1.645. So we have to calculate the Z using 77 as our sample mean, and then we're going to ask what the Z is and whether the Z is greater than 1.645 or not. That's what we're doing. And just before we get to having you do the calculations, I'm going to sort of talk a little bit, how would you do the study? So it'd be pretty easy. So they've done studies like this experimentally. And so with ego threat, how they manipulate ego threat is in this way, essentially. They have you do a task. They have you do something. Let's say it's a task or like a problem that you have to solve or some sort of quiz you need to take. And what they do is they give false feedback. And so there's 2 conditions in the false feedback. One is, you did really good on this task. You did better than 95% of the people that take this task. You're really smart. So there's no ego threat whatsoever there. In the other condition of ego threat, so remember ego threat is over here, or ET, ego threat. Under that condition, the feedback is, you did really crappy on this task. You did only better than 5% of the people. So 95% of the people that take this task do better than you. So, and it's false feedback. You rig the thing. So they do the same thing, but then you give them the false feedback. You're really smart. You did it better than 95%, or you're horrible. You're dumb. You only did better than 5% of the people. So that's how they manipulate ego threat. And then what they do is they give people chances to aggress against somebody. One study they had is the person thought they were shocking the other person. So they were actually able to measure very quantitatively the intensity of the shock and also the duration of the shock they were giving people. And by the way, in that study, narcissists, if they had threatened ego, they shocked the heck out of the people. They gave a higher shock level, and they gave it for a longer period of time versus the narcissist who didn't have their ego threatened. So that's how they manipulate that. So let's go back to the problem. So there's your data. You have the sample mean is 77. So that's the treatment group. The sample standard deviation is 10. Use that for your standard deviation. The sample size of the treatment group is 50. Use that for the N. And then we have that estimate of the population mean. That is 60. Go ahead and do step 3 4, and 5. Don't worry about step 5 if you're not quite sure what to do. We will review that. That's the toughest part. So go ahead and test this hypothesis using this number with a one sample z. And remember that the one sample z looks like this. So remember that 77 is the sample mean. 60 is the population mean in this case without the treatment. 10 is the standard deviation. And 50 is the n. So you just plug in the numbers there. I'm just double checking it's on. Yep. So we have the sample mean of 77. So that's the mean aggression of the narcissist with ego threat. 77. The mean level of aggression for narcissists not under ego threat, the placebo group or the control group, was 60. So the numerator is 77 minus 60, that's 17. So we're in the right direction. It's a positive z-score we have. So our standard deviation was 10. And we had 50 people in our treatment group, so use that n. So we take the square root of 50. So we have 10 divided by the square root of 50, which is 7.07. And so our denominator is 1.4144. So we take our numerator of 17, we divide it by the denominator of 1.4144. Our one sample z is 12.02. This is our one sample z. I just want to put this there. By the way, we italicize statistical symbols. So that's our one sample z. So that's step number 3. We calculated our one sample z. Now we have to go to step number 4, where we make a decision about our HO. So remember, in our decision for HO in step 4, we're going to take what we calculated. So we calculated 12.02. That's from our data. And then we're going to compare that number with our decision line that we had, our critical value, which was right here. Our critical value for our z was 1.645. So that's always going to be for our one sample z. The 1.645 is always going to be there. So our thing that we calculated from our data, sorry about that, what we calculated from our data, that z is greater than that little line thing that we drew, our critical value of 1.645. So we reject the HO. We reject the HO. It says that something's going on. There's an effect. Ego threat changed the level of aggression. So I'm just going to show that again. So ego threat changed the level of aggression. So, you know, we had a z-score of 12.02. I'll be really precise here. So our z-score was here. That's way down here somewhere. That's way down at the tail. So we crossed the line. We're further. Our ego-threatened narcissists were much more aggressive than they needed to be to say that something's going on. That ego threat changed their aggression. We crossed that line. That 12.02 is way over here. So we're way over here. We're farther away from the placebo group than we need to be in aggression. Something's going on. Our ego threat manipulation changed their behavior. So we reject the HO. Then we write it up. And so with the write-up, again, this is going to be maybe the toughest part to learn. But start simply. Start with saying in words what you found. Well, you know, I'm going to look at this diagram again. We found that our ego-threatened narcissists were way more aggressive than the narcissists in our study that weren't threatened in terms of ego. And so I just say that. And ignore the means and standard deviations for now. Ignore the parentheses. So narcissists are more aggressive under conditions of ego threat versus not under ego threat. So just think about that sentence again. So narcissists are more aggressive under conditions of ego threat versus not under ego threat. So in that little statement, we want to say, what are we studying? Well, we're studying narcissists. And what's our DV? Our DV is aggression. Well, what was your IV levels? Well, our IV levels were ego threat versus not ego threat. Well, okay, so you're looking at narcissists aggression, ego threat versus not ego threat, which one was higher? Ego threat was more aggression versus not ego threat. So you also give a direction. So in our little simple statement there, we want to say what our DV is, aggression. We want to say what our IV was. In this case, we have the IV of ego threat versus not ego threat. And then we say, if there is a difference, what the difference is. Ego threat had higher aggression than not ego threat. So again, that's basically how you write that sentence. If this is seeming a little bit hard, that's okay. This is the first time that we're kind of doing this. You're going to catch on. But try to follow that format. You want to say what the DV is. In this case, there's two groups. There's ego threat versus not ego threat. Which group was higher? Ego threat was higher on aggression than not ego threat. So try to remember that sort of basic form. Whenever we have groups, we want to give a mean and standard deviation. So we have two groups here. We have narcissists under ego threat. Their mean level of aggression was 77 right here. They had a standard deviation of 10. So when we have a group, we want to give their mean and standard deviation on the DV. The DV is aggression. We also have another group. We have a group of narcissists who aren't under ego threat. And so we give their mean and standard deviation also. And then at the end, we put a little parenthesis, comma, sorry. And then we say what the stat we did. Well, we calculated one sample Z. Well, what was the number that we calculated? Well, it's 12.02. And again, if we reject the HO, we say P is less than 0.05. P is less than 0.05 tells the reader that we rejected the HO. Some effect happened with our ego threat. And we're just saying with the P is less than 0.05 that there's less than a 5% chance that this difference between the ego threat group and the not ego threat group on aggression is just due to dumb luck, which means there's a 95% chance that it's due to our manipulation of the ego threat. Okay, so we're getting towards the end of this lecture, but we have one other thing to talk about. And again, sort of the caveat of this whole lecture is this is our first foray into inferential statistics. And so don't worry if you're not catching everything. This stuff will click with more time that you have on different problems as we go through the semester. So we just taught you what's called null hypothesis statistical testing, which is this whole thing about the line, which I think I still have. It's about this probability. You know, what's the probability that you would have a ego threat aggression score way over here? What's the probability? Well, the probability is less than 0.05. That's what we mean by null hypothesis statistical testing. So there are criticisms of this approach. It doesn't tell us everything. Basically, I'm going to put this as simple as possible. Remember that sample size means a lot with inferential statistics. So the larger your sample size, the more pieces of information that you have, the more confidence you have making inferences from the sample to the population. You make better predictions. More pieces of information, more dates with a person, you make better predictions about whether it'll be a good boyfriend or girlfriend. So the problem with that, though, is if your sample size is pretty decent, and we're talking from 50 to 100, not very large, you could find a very small difference in the groups to be significant. Because the larger your sample size, the easier it is to find an effect. It's just saying that it's a reliable effect. It's reliable because we have a lot of pieces of information. But the problem is does that mean something? So I would guarantee you almost that with a sample of 100 people, a difference in height of, like, let's say 1/4 of an inch would be significant. Because with 100 people, you could probably say that, yeah, this is a difference between the group. It's just saying it's reliable. It's repeatable. It's a good probability that they're different. But it doesn't say anything about how large the difference is. So is a 1/4 inch height significant in real life, or meaningful in real life, I should say? Maybe not, unless you're a basketball player. And so we have this thing called effect size. Effect size tells us how big the difference is. And Cohen's d is the effect size that we use. Don't panic. This should look very familiar. Remember the Z formula? And I'm going to actually write it down. I'm going to get rid of this. Before you panic when you see a new formula, I'm going to tell you it's not a new formula. So remember our old Z formula where we did this on the exam. We took a score and saw how far the score was from the mean. But we said, well, that doesn't mean anything. We don't know exactly how big that is. We don't know how big it is unless we standardize it by dividing it with the standard deviation. Let's look at the Cohen's d formula. It's the mean of the treatment group minus the mean of the no treatment group divided by the standard deviation. So, whoops, sorry about that. So the difference between two things divided by the standard deviation. So the mean of the treatment group, in the example we just had, the narcissist who had ego threat, minus the mean of the narcissist who didn't have an ego threat, the placebo group. Is that really a big difference? We don't know unless we standardize it. Same formula. We don't know how big that difference is between two groups unless we compare it to the standard deviation. That's all we're doing. We've done that before. So that's what Cohen's d is. It's just like what we've done before. And then that number tells us how big the difference is between those two groups. So if it's 0.2 and below, it's a small effect. It's a small difference between those groups. If the d is 0.5 to 0.21, I guess, it's a medium effect. It's a medium difference between those groups. And then if the d is 0.8 or above, we say there's a large effect. There's a large difference between the groups. And when we say large, we say it's in magnitude. In real life, it looks like a big difference. Because here we don't care about sample size. So sample size doesn't come into an impact in effect size because sample size is just for the null hypothesis statistical testing. The p is less than 0.05. So only in terms of probability sample size matter. Here we take sample size out of the formula and we just care about the difference between the two groups. Well, we don't know how big that is unless we standardize it by dividing it by the standard deviation. So pretty easy. So it might look difficult, but it's pretty easy. So let's take the narcissist example. So remember the mean of the treatment. So we need the mean of the treatment minus the mean of no treatment divided by standard deviation. Mean of the treatment when they were under ego threat, the mean for aggression was 77. Mean aggression under no ego threat, so no treatment, was 60. The standard deviation was 10. So we simply take treatment mean minus the control or placebo mean divided by standard deviation. 77 minus 60, 17. 17 divided by 10 is 1.7. 1.7 is a large effect. It's more than 0.8. So we would say not only we found that, remember, it was significant. So not only there was less than a 5% chance that it's due to luck. So there is something going on. Narcissists in our sample acted more aggressive under ego threat conditions versus not ego threat. And our statistics says that that's something we're 95% confident that is true for all narcissists all over the world. So that's our statistical test in terms of the null hypothesis. But not only our null hypothesis was rejected, remember at the top, we also have evidence that the difference between the treatment group and the non-treatment group was large. There was a big difference in aggression. So that's saying that ego threat made them act a lot more aggressively than under regular conditions of not ego threat. It had a large impact on their behavior. That's what effect size is saying. You can ignore that. I'm going to ignore that too. You can ignore this one too. You can ignore this one too. We can ignore this. We've talked about this. So just ignore this. Ignore this. We've already talked about this. And I'm worried about trying to shove too much down your throat. So don't worry about this for now. We'll talk about these issues later. Don't worry about this. Don't worry about this. So I'd like you to now do homework number 5. It should be relatively easy. There's 2 Z problems you have to do, and I should probably 1 sample Z problems. 1 sample Z problems. And there should be nothing here. So it should be relatively easy. So if it took you like 5 minutes to do the sample problem with the narcissist, your homework should take you about 10 minutes. So 10, 20 minutes, I hope it will take you to do the homework. And I will talk to you in the next lecture. And what we're going to be doing in the next lecture is that we're going to go from this 1 sample Z score, and we're going to go to a statistic that we use very commonly in psychology and social sciences, and we're going to get into the actual world of what we really do in statistics in social sciences in the next lecture. So I'll talk to you then.